Let's see. Okay. So we know we can have the more general situation with directions on edges. And for directed graph, as you see, that quite different from undirected ones. The matrix involved is not symmetric. Eigenvalues are not real. So for undirected case, we have tools from spectral graph theory. Random walks, if you look at those books, mostly are on reversible Markov chains, and you have eigenvalues to bound the rate of convergence for random walks. And we have Cheeger inequality, which controls these partitions and local partitions, sort of main tool to analyze these. And we don't have any of that for directed graphs. Since I wrote a book on spectral graph theory, the most inquiries I got is to ask about the directed case. So in the last few years, I was looking at the directed case. And you can see that for the Cheeger inequalities, well, undirected graphs has all sorts of applications because of the cuts, partitioning, and so on. But most real-world graphs are directed. This is the BGP routing graph, border gate protocol routing graphs. When you route one message to another, of course, it's directed. And this is from another student, the instant messaging network, also directed because you send one message from A to B. So what about Cheeger inequality for directed graph? But before we get to that, we have to get through a few hurdles, right? So what do I mean eigenvalues there? What do I mean Laplacian there? What do I mean Cheeger constant there? And what do I mean, what are their relation to random walks? So there's quite a bit to do. We can define directed graphs, the transition probability matrix, if we take this to be typical ones, or you like the weighted version. So for such a random walk, there's these typical questions, right? If your random walk will converge or not. If it converges, what's the stationary distribution and how fast you get there? And if you have some quantity, like eigenvalues, to be able to control how fast you converge. So these are really sort of mathematically sort of histories. Can you hear the shape of a drum? You want to say how fast and slow things are converging. But now we have these directed drums, okay? All the edges have. And instead of using eigenvalues here, we need some quantities, right? Okay, so here is the outline of the graph. We're going to define the Laplacian there and get the Cheeger's inequality proof there and have discrepancy inequality proof there, which is different from Cheeger inequality, so a stronger version. And then for graphs, usually we have tools. If the graphs is very nice, with great deal of symmetry, then you can use group representation. I think in earlier talks today that we heard some from Percy's talk. But in fact, for directed graphs, semi-group methods coming in. But if we get to that, and then there are problems, right? But I couldn't help because I spent some time here in the last 2 months, surrounded by a lot of people with new results on Cheeger inequalities, higher order Cheeger inequalities. So I was trying to read those papers and try to update my book, right? And some of these proofs are pretty difficult to read. In fact, I'll do a survey. Those are very nice hierarchical inequalities. So people here all know about hierarchical inequalities. Can I see a show of hand? Yes, okay. How many people really read those papers and understand the proof of those couple of papers? The authors definitely did. They're not easy to read. My students have a reading group, try to help each other, and they're not easy to read. Anyway, I'm going to give you short proofs. Very ambitious here. If you have read that paper, then you really appreciate short proofs. If you haven't read, then you really, really appreciate the short proofs. Okay, so before I do the short proof, I have to say what the matrix we are talking about, right? If it can be used to capture the properties of the graph. And we are going to use normalized Laplacian. I think here people use normalized Laplacian so often. I was really very happy because when I first write my book on I realized normalized Laplacian is good to capture subgraphs and so on. But for many years, most people in combinatorics love the eigenvalues for adjacency matrix instead of normalized Laplacian. But now it's really being used quite a bit more. Okay. So one reason for using it is that it's sort of a symmetrized version. Really 1 minus the eigenvalue of the transition probability matrix. But it's symmetrized, so we don't have to worry about left eigenvalue, right eigenvalue, and right eigenvector, and so on. And in particular, the spectral gap, lambda 1 is the first non-trivial eigenvalue. That's this one gap here. Which gives a great deal of information. It gives the topological information about connectivity, but also for undirected graph, one thing I want to point out, it has very nice lower bound. 1 over the diameter times the volume. If you have simple graphs, this is like n cubed lower bound, 1 over n cubed lower bound. So your random walk, really, the rate of convergence, it's all polynomial rate. It's nicely in the polynomial land. Okay. What is the story for? Okay. So one thing that's useful about eigenvalues is that we can control the diameter, actually. So if you think about diameter, which is how many hops you need to reach one vertex from another, right? And the diameter is the longest distance. And you can use eigenvalue bound to, you can use eigenvalue to bound the diameter. Okay. And what we want to do is to carry all this to the directed case. There's also this general notion of isoparametric. So it's really coming from, you want to use a short curve to enclose a unit area, say, in the plane. Then we all know you should have a circle, right? But in a graph, then we have the situation you want to bound the number of edges leaving versus what? One way to do it is define the volume of a subset to be the sum of the degree versus the cardinality. And we are going to use this version. Which is particularly suited using normalized Laplacian. But also for general graphs, we have big degree and small degrees. And the eigenvalue here, you see the top and bottom both are counting edges versus here counting different things. Okay, the Cheeger ratio for a subset here, we'll just have a definition here. And Cheeger constant of a graph is you have a subset and you have its complement. You pick the big one, which is the same as you which is the case because they share the same boundary, which is the smaller part. That's HS. Okay. I use this notion, this notation, so we can go up to higher ones easier. And this Cheeger constant is in some community called conductance. We have to, the first person used this definition certainly didn't quite realize that Laplacian has a lot to do with electrical networks, which conductance has a different definition. So fortunately, this lecture, we don't do electrical networks. So okay, Cheeger inequality says that the eigenvalue is sandwiched by the Cheeger constant and its square. I think now in some paper they like to write this version, but it depends on what you care about, eigenvalue more or Cheeger constant more. Okay, sort of cleaner this way. Okay, higher Cheeger constant, I'm also going to define it. So you have disjoint K subsets, and you take the max, minimax. And in the case of H1, then that's the same thing. Okay. So there's recently this, we're really happy to see very nice work about higher order Cheeger constant. Or it's very often you see like this.
Better on the right, it's K squared. On the left, it's K.
I know. That's called cheating, hiding the powers, okay? Let's honestly writing it this way. Okay. So what I want first to do are these short proofs, right? So let's do very short proof for the Cheeger inequality. This will be in my updated book. Okay, but before I do that, I need to do characterization of Cheeger constant. So one way to do the Cheeger constant is that instead of Dirichlet sum, which are two norms, here we have one norm. This is just the absolute value, sum over all edges, the difference of the function point, okay? It is in my book, actually, chapter 2. And you take the C, you shift around linear replacement, pick the best one. Okay, so this is a characterization of Cheeger constant and its equality. It's equal. The first remark, the supremum for the C really should just take it on the medium, which means the value that have the volume on the left, half volume on the right, almost. The second remark is that this really gives an algorithmic bound, upper bound. So this is inf, right? If you pick any f, you get an upper bound. If you just pick this this medium in the middle, okay? And because what happens is that for f, you give one linear arrangement of all the vertices, and these edges stretch around, and you look at the smallest cut, the minimum. Okay, here you look at the number of edges going across. You look at the Cheeger ratio over there. So I have a typo here. Really, you look at all the subsets on one side. For all those subsets, you look at the best Cheeger ratio. That's the alpha f. Okay, so it's really an algorithmic bound if you can find a good f. So while we are talking about Cheeger inequality, one nice thing is that it's actually an algorithmic proof because the best cut gives you that lower bound, which means it gives you that performance guarantee. You find a cut with that kind of guarantee. Okay, so here's a very short proof for Cheeger's inequality. So the top line is just from the definition, right? And here you can have the medium in the middle. then I do one round of, this is nothing, right? Just a definition. I multiply the same thing on top and bottom and Cauchy-Schwarz, then I'm done. Much neater than at least the proof I have in my book, which will be in the new revised version when I'm sitting down to do the revision. So that's have a couple lines, right? If you accept my Cheeger constant characterization. Now I want to do higher order Cheeger inequality. I need two things. The first thing is a weaker characterization of Cheeger constant. And the second thing is a partition into expander. Okay. So instead of this Cheeger characterization, I am favoring those f, which fx dx sum up to 0. In that case, I give up a factor of 2. But still, it's pretty good. So instead of the medium, I'm choosing this one, which is, from the linear algebra sense, more favorable. Okay. So I'm going to use this weaker characterization by giving up a small constant 2. And then guess what? I also need this partition into expanders, which is very nice result of Luca and Shire. So basically, what it says is that basically for any k, okay, you can find smaller k which has a big gap, okay, and in that case you can partition into L parts. Each part, the inside Cheeger constant. This is not exactly the Cheeger constant for the induced subgraph. See, because the induced subgraph volume is a little different in the induced subgraph. I'm sticking with the old volume, okay? This ratio is big. So it's not Cheeger ratio for the induced subgraph. In the paper quote, it's not exactly right, but it's not too far off, okay? Because I'm using the old volume in the whole graph. So almost like it's also H star. It's not H in the induced subgraph. So I'm going to use this. So I'm a little bit cheating, right? I'm assuming these two things, the recharacterization and the partition into expanders. But I have to say that the proofs for partition into expander, that paper is much easier to read than the previous two higher Cheeger inequality papers, at least for me. Maybe someone will argue with me. No? Okay, so this is a short proof of higher order Cheeger inequality. So here I'm going to, this is, I can write it as a soup inf. This is just the usual definition, right? One of the definitions. So I'm going to choose these, I'm going to, what do I do? Oh, this is nothing. I'm just going to write it into this form. The top is the L is D minus A, right? Okay, right now I'm going to choose my phis. So this is soup, so I'm getting inequality to be characteristic function with these for these subsets. Which means I am using that partition into expander result, okay? And here, Fi, I'm just going to choose them to be like just the restriction. So this whole top, the Dirichlet sum, you can write it like this. And the bottom, because it's disjoint basis, so I have this inequality. Then on each piece, I just do my argument like my previous slide, then everything falling out. Then all I have to do is to add lambda k and L less than k here. Then I'm done. That's the proof. Any questions? So I am slightly cheating in a sense. I'm using this partition into expander result. But that's a very nice result. But with that, I can get Cheeger inequality on one page, higher Cheeger inequality. James, any question? See your phone there. No? Okay. Then, yes, Richard?
Does this also give an alternate proof of the just the k equals 2 case? So if you have two expanders, does the proof look this? So I noticed that you don't have a step of Cauchy-Schwarz happening here. So in the two expander case, are you saying that I just plug in test vectors and that lower bounds mediated? That just using.
Well, for the case of two parts, we are using bigger tools than it's needed because look at this constant C,
So,
you suffer there, right?
but where are you getting around the Cauchy-Schwarz step? That's what I'm trying to understand.
No, Cauchy-Schwarz still here. Okay. Because here, from here to here, I'm using the Cauchy-Schwarz. I'm using the same argument as the previous page, which has the Cauchy-Schwarz.
Maybe there's a square missing at the end. HK.
Oh yeah.
HK is
I think it is okay. This part to this part, I get a square. Okay.
Near QED.
Oh, I lost something. Oh, sorry. Okay, I lost. I forgot this. That's a typo. Just did it today. Okay, so now we can go back to the directed graphs. Getting these Cheeger's inequality for undirected case away. Okay, so for directed graph, I'm going to use the transition probability matrix. Okay. So there's a Perron-Frobenius, right? So it says, so basically, if you look at the adjacency matrix, well, for the directed graph, just a general matrix. And if you want to use Perron-Frobenius, then if you get a unique left eigenvector if the graph is irreducible, which really translated to strongly connected. So suppose we assume the irreducibility. So once you have that, let's look at what the stationary distribution means. Phi p equals phi, right? So it's a left eigenvector versus 1 is a right eigenvector. So the first thing about directed graph, the big difference from the undirected ones is this Perron vector, the stationary distribution if we have one. Just by some example, very easily constructed, you can see that the distribution of phi can be vastly off. See, for undirected case, it's proportional to degree. So the biggest one and the smallest coordinate is only off by a factor of n at most, right? It's only polynomially off. But guess what? In this graph, the stationary distribution, exponentially off. So, which means the smallest part is exponentially small, possibly. So you might say, okay, this construction has one very big in degree and small out degree. So it's so lopsided. No wonder the stationary distribution is so exponentially lopsided. Okay, I will construct this graph. So the in degree and out degree are very friendly, right? The in degree and out degree only off by a small factor, bounded degree, bounded ratio, okay? And guess what? This graph is just also exponentially lopsided for its stationary distribution. Yeah, so that's a very big difference. In fact, it could be as bad as n-1 factorial for simple graphs, which means all the edge weight is 1. Okay, so that's a very big difference. Just the stationary distribution for directed case is very unfriendly. Okay, it's not in the polynomial land in the worst case, of course. If we want to talk about convergence, then we also need this property of aperiodicity. We need, if it's has like a cycle, then it's going to oscillate. Your pebble is not going to converge to stationary distribution. But with these two conditions, they turn out to be necessarily insufficient to imply convergence, and then you have your unique stationary distribution. So we are going to assume from now on in the rest of the lecture our graph is strongly connected and with this condition, it's acyclic. So which is a less serious condition. Irreducibility, its connectivity is essential, but aperiodicity, very often you can do lazy walks to get away from it. So, but anyway, let's assume our graph has a unique stationary distribution. Okay, then we are looking at our cuts, right? We have a subset S, and we are looking at the out boundary, which are the edges leaving our area S, okay, with arrows pointing out. So we are going, this is just a definition. A circulation means this F is a function assigning values to my directed edge. So, and if I think I lost a few view graphs. Oh. It is a circulation if for each point the incoming vertices you sum up its F value is the same as outgoing edges, you sum up the F value. Then it's a circulation. If it is a circulation, then I can talk about the subset, the F value on a subset of edges. Then you're just summing up its value on the edges. And if it's a circulation, then if you have a subset and its complement, then the boundary in either direction is the same, if it is a circulation. So I apologize. I missed one view graph, which is the definition of circulation. So if you, okay, so if you accept this, okay. So I am going to define the circulation with respect to phi. If you have a stationary distribution, I'm going to use it to define a circulation. Then I can define the Cheeger ratio. So I actually have a few examples, right? So for some graphs, the Cheeger ratio is quite friendly, have a lower bound, okay? But for some graphs, this could be very. Now here I want to define the Rayleigh quotient. The Rayleigh quotient is this one. remember usually we are taking, okay, so where do I define the Laplacian? I'm going to use my stationary distribution, this phi, to define the I'm going to, so this phi is really play the role of d in the old days, right? But I'm off by a scale. A little bit short of giving my definition right. I'm trying to find my definitions. Okay. So let's try to forget about this. I just look at this one. Okay, so remember for undirected graph. So this is really generalization for the directed case. If your directed graph for every edge you take one in both directions, we should uncover our undirected case. So look at this. So this guy here really play the role, like for undirected case, it is the so this is D inverse A, right? So this is like canceling out, okay? So basically it is this one. That's the Laplacian. If I normalize it a little bit, okay. I'm cramping too much definition. Okay, so basically I'm using the phi here, this Perron vector, to modify my transition probability matrix, and this one is its transpose. So you can see this Laplacian, after it's defined, it is symmetric.
Isn't that what we call the additive symmetrization in my papers from the 1990s with Salov-Cost?
It is possible, but I think a lot of previous definition very often just take PP transpose, because mostly deal with
transpose in the L2 norm,
right.
given by the stationary distribution, and so it's the
right. So
additive reversibilization.
In many papers, it's only deal with the regular graph, right? Okay. Okay. For regular graphs, in fact, I think for regular graph, it's just PP transpose on the top, but you have to divide it by the scale it up. In fact, I think with this definition, then we can get our Rayleigh quotient, which is sort of coming back in the form very similar to what we see in the undirected graph. And my main point is that using this definition, I'm pretty sure trace back to Percy's paper, and even in some of Persa's paper have similar form. But the point is that the eigenvalue there, we can get Cheeger inequality. And one good thing about this eigenvalues is that we can also use it to, this is a useful lemma. So basically, these eigenvalue, if it is non-zero, if there is a gap here, then we will be able to bound the singular value of this normalized form. And the consequence of that is that we can bound the total variation distance here. So basically, you can get total variation distance this back to the undirected case. It's the inverse of lambda at the rate of the c. But this term shows up, the log of this minimum degree, which could be pretty exponentially small, right? But it is behind this log, so it's not too bad. Okay, and you can use this to get the diameter bound also. I'm not going to do the proof. I only want to say for undirected diameter eigenvalue inequality is like this. Okay. For K regular graphs. For general graphs, your lambda, doesn't show up. For regular graph, you get a eigenvalue bound there, so it's of this form. For expander graph of degree d. But for the directed case, there is off by a factor, which I would love to get rid of. You might say, you might say you don't quite care about this factor. But if you see from the different point of view, for the extremal problem in combinatorics, if you fix the diameter, you argue about how the extremal graph, how big the graph can be, then you'll blow up exponentially. So, actually, interesting to deal with that constant. I don't know how much time I have.
11 minutes.
Okay, in that case, it's not so bad. We can still go on a little bit. So for usual undirected graph, very often when we are talking about expanders, they are really have many implications. Many people might think it means neighborhood expansion, rapid mixing, okay? But really, if lambda 1 has a gap here, then from Cheeger inequality, you get neighborhood expansion and rapid mixing of the lazy walks. On the other hand, if your lambda 1 is close to 1, that is a much stronger situation, very different from this part 1. When people talk about expanders, so is that this properties or is that this properties? It depends on different papers using different definitions. But the fact is that if the lambda 1 is very close to 1, then for this family, for graphs with this property, it's really quasi-random. So one way to say it is that, see, if you care about controlling the edges leaving a graph to its complement, okay, that's Cheeger inequality in place, right? In the other direction, you take any two subset and you want to bound the number of edges in between. See, that is just a small special case. Right? This, in order to control this, that's a discrepancy inequality. In order to control the discrepancy, you need the eigenvalues lambda 1 close to 1. Okay, it's a much stronger notion. It is so-called quasi-random. It is equivalent to a bunch of other properties. large equivalence class of graph properties that each one implies another, almost like in theoretical computer science, you talk about equivalence of computational complexity, NP complete and so on and so forth. But for these random-like properties, for actually any graph properties you would like to find its right classification. And these are the quasi-random properties. So the one usually try to do at the beginning is to bound the number of edges in between by edge density times x and y. I think I mentioned this before, but for those who haven't heard, that see, this inequality is only good if O1 vector is a good approximation to your your principal eigenvector, and in that case, you can get an approximation. In a general case, if the graph is not almost regular, these are no longer the projection to your main eigenvector, then really the right approximation is this normalized form, the volumes coming in. Okay. And for that, we can also, let's skip this. Okay. So the discrepancy inequalities for directed graphs, we can also use eigenvalues there to control the discrepancy inequality. But all the edge weight is modified by, is defined by using the Perron vector. If we do that, then you can control the flow in between x and y. So we also have a set of discrepancy inequality for the directed case. Of course, as you can see, it all depends on the Perron vector quite a bit. So this is Franklin is here in his thesis dealing with such discrepancy inequality for directed graphs. So I'm not going to have time to talk about the semi-group spectral methods too much. I just want to end by mentioning some of my favorite problems on directed graphs. There is one. In fact, there are many problems very simply stated for digraph that we don't know versus in graphs. So here is another one. Tons of curious combinatorial problems. So what is this problem? Oh, we want to determine that. We want to get the right order of f of a. Find a long increasing path. Graph with the edge labeling. One of my favorite problems. Okay, I think I'm going to stop here.
Questions? For the last one, what is the question? GV.
The question is to close this gap. I think I'm missing one. the conjecture.